All right, everyone, let's get started. Can you confirm that you can hear my audio? All right, thanks, everyone. So hello, everyone. My name is David Ruck. I'm here at the University of Maryland, and welcome to Cytometry in R. And today we're now on the sixth week of our Cytometry in R course, and at this point we have slowly but surely built out a pretty solid foundation of just general R knowledge, and we've been learning how to apply it to our flow cytometry data. So this week we're exploring how to use the ggplot2 package, which allows us to create plots within R. So while we're thinking of many different types of plots we normally use in the context of flow cytometry data, ggplot2 and other similar R packages that extend its functionalities allow us to create a wide range of visualizations, ranging anywhere from statistical style plots to drawing maps to building informational graphics that you would typically see as in a magazine. So one of ggplot2's core strengths is its utilization of the grammar graphics concept. Rather than treat each type as plot as its own separate entity and have to rely on separate types of functions to build them entirely, you're basically breaking down the individual elements of these plots into what's known as a layer, whereby if you combine the different outputs together, you can build out a desired level of a plot. So this abstraction kind of process permits us to construct a wider range of plots from the same data set by just simply swapping in a couple functions here and there and a couple arguments rather than have to build out completely different things for each individual plot style. So the concepts we'll be going throughout today, we'll be looking at the individual layers that make up a ggplot2 style object. So when I first envisioned this lesson, I wanted to go big. I wanted to show you how to do a dot plot. I wanted to show you how to do a line graph. I wanted to show you how to do flow cytometry plots. But in getting everything assembled, I realized that'd be a little bit overkill, trying to put everything into a single lesson. So we're going to focus mostly on a dot/box plot style, but these are equally applicable when we start looking at other styles of plots over the next couple weeks. So the main things in thinking about these individual layers of a ggplot object, we have the data and the mapping layers, which kind of dictate which data from our data frames or our matrices we're actually using for these particular plots. Then you have the layers and scales, which impacts how we visualize them, whether it's a dot plot, whether it's a violin plot, etc., etc. And then there's the more cosmetic changes where you're changing things about the facets, the coordinates, and the theme. So we'll be going through most of these today, at least as a brief introduction to what we have in the form of the syntax that ggplot uses when assembling a plot. As we do every week, I have updated the course Cytometry in R folder, so you should go ahead and sync your forked version of the Cytometry in R project repository just to make sure you get those updated changes. And then once that's done, just pull them in locally with Positron so that you have them on your local computer. If you're following the organization scheme we've been using throughout the course, all you need to do is then copy over the data from the week 6 folder in Cytometry and R over to your own project repository. If you're naming it just like we've been doing, it'd be week 6. And this should help prevent some of the merge issues that we've been encountering throughout the course. All right, and let's do a little bit of preparation before we actually dive into the plotting. So we'll be using dplyr pretty extensively throughout this session, so we should go ahead and attach it to our local environment via the library function. Now, when we're loading in dplyr via the library call for the very first time after we've restarted the computer, oftentimes we'll get a little message that looks something like this. Attaching package dplyr, the following objects are masked for package stats, and then it lists the two function names, filter and lagged. And then you'll see something similar where the following objects are masked for the package base, and then it will show you the functions names of that are being masked: intersect, setDiff, setEqual, and union. So what's basically happening behind this message is that both the dplyr and the stats packages contain functions that are named filter and lag. Since stats is a base R package that gets installed with your base R installation, it's always loaded by default. So when you go ahead and attach dplyr via the library call, all of a sudden you have two packages that contain identical names that are active in your local environment. Consequently, if you ran a single line of code that contains either filter or lag, R would not know which package is actually being used for that particular line of code, and confusion could ensue. So to avoid this, what happens when you load in dplyr is for both the base R, stats, and base packages, those that contain identical names, the functions that have identical names to those that we find in dplyr, these are masked, i.e. they are hidden, so that only the dplyr functions with those same names are actually being used, so that they are prioritized when the code is actually run. So, continuing where we left off, during week 4, we were looking at a tidyverse data set, basically seeing how we could mutate, we could select, we could filter different rows and columns. We'll be continuing with most of that data set for today when we're looking at ggplot2 objects. And then at the very end of today, we'll look at the week 5 data set where we loaded in a Flojo workspace to R as a gating set via the CytoML package. We'll bring that data set in and reuse it when we're actually looking at how to do the cytometry style plots. So just remembering how to do this, since it's been a couple weeks, we are keeping the organization scheme that we've been following throughout the course. All those files should be within the data folder. So we start creating our file path using the file path argument. We specify that it's within data, and we assign this to an object we're calling storage location. We're using this location as part of the list.files function, and we're searching for anything that matches the pattern.csv. And just remembering, we want to make sure we have the full file path between our working directory and the location those files are being stored. So we're setting that full.names argument equal to true. And then we're assigning this over to the value object, the CSV. And then we're passing that particular value to read.csv function, which will then go find that correct location, read in the file, and this is how we end up with the data frame we saw a couple weeks ago when we're looking at the tidyverse functions. As you can see, it's kind of typical of the downstream of a flow cytometry analysis. All the individual tubes are present as rows, all the floors, not all the actual derived statistics are present as individual columns, as well as we have some metadata columns toward the very top of the data frame. So let's just quickly get refamiliar with this data set, which is often helpful when it comes to trying to plot whatever we're trying to plot. So let's check to see what kind of values are present within each of these columns. So rerunning our old friend, the str function, we can see that there are 31 columns, 196 rows, and then we're looking at these individual columns. We can see that some of them are characters, some of them are numeric style, and it can be kind of convoluted just trying to figure out what you're working with. So the main important thing when working with ggplot2 columns is that you need to know what kind of values are contained, because this will affect whether you can plot them as you're treating a continuous numeric variable, or if you need to treat them in this particular way. So being aware of what your data looks like before you pass it to the plotting functions is quite a useful skill to have. So if we're looking at this right now, we can see there are several columns that are present as character columns. Now, if we just wanted to grab just those character columns, we could reuse some of that information we had from a couple weeks ago. Just scroll through SDR, see what the individual names of those columns are, and just kind of add them into the select function. And then we could isolate out just the character columns. Well, this certainly works, and you could certainly do that. It's not necessarily time-saving a method of being able to do it. So it'd be much better if we could basically select based on the type of values that a particular column contains to make the process of identifying which of these columns is much easier. So fortunately in R, we can do that. We just have to combine a couple of functions that we already know with another function we're going to introduce. So namely, over the last few weeks, we've looked at the is.character function, which will basically check something and tell us whether it's a character or not, whether it's true or false. But if we place that in the middle of the where function, which is a function that dplyr actively borrows, i.e. it exports from the tidyselect package, we should be able to kind of combinatorially narrow in on these character style columns. So the way this would work is, once again, we have our data set, we're passing it through the pipe to the select function, And then select is what's going to be grabbing those individual columns. And what it's basically doing here is the where function is checking to see, is the particular column a character? If the column is a character column, is that character will return as true, and therefore where will end up selecting that column. So by combining these two arguments together, we can basically identify and select just the character columns that are contained within our data frame and leave all the logical and all the numeric style columns out. And this way you can down select for what you need. Vice versa, we don't have additional type checking functions beyond is.character. We could also use these if we just wanted to select, for example, the numeric values. And we just, by introducing isNumeric into that location, we basically selecting all those integer style as well as numeric style, depending on whether they have a decimal point or they don't have a decimal point. And vice versa, we could try it with the is.logical one, but in this case of this particular data set, there's no logical columns present, there's no true or false, so we come back with an empty data frame. Now, if we look at the str output we just had, we can spot that our date column is currently showing as character values. So if you go back and you scroll into where we have for date, you can see it's showing up as character, and it's currently formatted in year, month, day style formatting. Now, character values, when they're plotted, tend to be treated as what we know as categorical factors. When these are plotted, they tend to default to arranging based on alphabetical order. So in this particular case, this is not going to be an issue. So if we pull the data from the date column and we sort it and just look at the unique values, you can see these are just being treated kind of in alphabetical order. 2025, 2025, 2025. It's continuing kind of similar as what we do for a lot of the different style formats. However, if you had a different formatting to your date, let's say instead of using year, month, day, you had day, month, year, this alphabetical reordering could cause stuff to be rearranged in ways that you don't actually intend. So for example, I gave some alternate format dates, and you can see when R was just reordering it based on quote-unquote alphabetical order, you can see now we have going from 2025 to 2026, back to 2025, and then to 2019. So your actual time progression on the x-axis would not actually be kept, and you would end up with a scrambled plot. So because of this, I generally recommend if you have dates or times within your particular data set, I recommend reformatting them into a date or time format. Within R, the tidyverse package LibreDate does the best job at reformatting these types of values to their own specific date or time value styles. In this case, what I recommend doing is once we load in the LibreDate package by attaching it to our local environment via the library call, we can basically make advantage of one of those functions it has, basically the YMD, standing for year, month, day. And what we're basically doing in this case is we're taking our data, we're using that little $accessor symbol to basically select a column, and we're basically selecting the date column. So at this point in time, those date column values are still showing up as characters, but after we pass them to the YMD function, they'll get converted into date format. And then basically what you're seeing here is this little assignment arrows writing back onto that same existing column, so we're overwriting the current contents of data $date. Sure enough, if we check SDR at this point, we can see that the format is showing up correctly as a date style value present within. So our plots will actually treat these as date style values when it comes time to plotting. Similarly, we can also look back at those numeric type value columns that we've just looked at briefly with SDR. And we have already discussed the differences between whether they're an integer, i.e. they're a whole number, or if they're double, meaning they contain a decimal point. But some of those concepts we covered way long ago in math class start coming back, namely, are those numeric values that are contained within a particular column continuous values, kind of like what we'd get back from our flow cytometer when it's like measuring the MFI of something? Or are they categorical, i.e. are they kind of discrete values that may be only a certain number repeated multiple times, but just in a numeric format? So, for example, if we look at this current data set and we look at the time point column, we can see that those numeric values are discrete. They're corresponding basically to the time month of the particular blood draw for the infants of the study, either at 0 months, at 4, or at 9 months of age. So this is not a continuous kind of column. It's very categorical, it's very discrete, it's very related to metadata, but R doesn't know that, so it may still end up trying to treat it like a different style column when it comes to plotting, rather than a something that you want to compare the groups against. So, One way we can avoid having this happen is we can basically tell R to treat the numeric values that we're seeing for these types of columns as categorical. The way that you do this is using the factors. You can convert them into a factor as part of the typo there. And the way you would do this is using the factor function. So kind of similar to what we just did with the YMD from LibreDate to kind of convert over our dates from character format over to a date style value. The same thing happens when you're converting something into a factor. Basically, we're looking at our data set, we're accessing the particular column that we're interested in this case, time point, and we're passing it to that factor function, and then we're overwriting that particular column with itself. And as you can see, time point factor has gone from being a numeric to now showing up as a value type factor, and it lists the tree types of levels present within, 0, 4, and 9. Therefore, R will know how to appropriately treat these columns when we're actually coming to the plotting stage. Now, this occurs when we try to plot. The reason I'm mentioning this is mostly because these are some of the kind of steps that we'll be encountering throughout the rest of the course. It's one of the joys of working in data analysis. You now have to be aware of what your actual data is, and a little bit more hyper-focused on, is it numeric, is it character, is it logical, is it discrete, is it continuous, etc. All these little things you didn't think you would have to do as a flow cytometrist start creeping back a little bit when it comes to looking at our data sets. All right, at this point, we have imported our data, we have refreshed our memory about the types of values that are contained within, and we have started to learn how to get things ready in R so that we can be able to use the ggplot2 package. So for this first plot, we're going to try to learn more about this general grammar or graphics concept, basically abstracting things into individual layers, and how we can use different arguments on these layers to build together eventually a type of plot that we want to see. So given that we're working already with downstream flow cytometry data, let's go ahead and try to create a box plot or something very similar, where we basically, let's look at those 3 individual time points on the x-axis for cord blood 4-month and 9-month PBMCs. And then on the y-axis, let's go ahead and do like frequency of T cells on the CD45 gate, so that we are looking at the difference across all the donors, all the time points, all the conditions, just to see what we can see. So we haven't actually done some of this data preparation yet, so we should go ahead and tidy our data. So just remembering what we did a couple weeks ago, we're taking our data, we're passing it through the pipe to the mutate function, and basically we have not yet gotten a T cell frequency column, so we need to go ahead and derive that. So we can take our T cell columns by count divided by this column for the CD45 count. At that point, we're going to get back a T cell proportion, which we're creating as its own column. Then we're passing that intermediate object through the next pipe to the next mutate function. And we're basically taking T cell proportion and timing it by 100 to get a frequency. And we're saving that to the new column, T cell frequency, which is then being passed again through the next pipe to the next mutate function, where we're just passing it to the round function to round up the number of significant digits just to a single one, so that it's much more concise when it comes time to plotting. And once again, it's overwriting on top of the T cell frequency within the mutate argument. And same thing, we're just going ahead and making sure that this particular data set is factored when it comes to the time point, so that we don't accidentally end up with a continuous value, although I will show what it looks like when a continuous value is passed in a couple minutes. So let's go ahead and get started. As with all our packages, we first need to go ahead and call library for the ggplot2 package. And then once that's done, the first layer of the ggplot2 is the data layer. So the way you actually use this data layer is you pass your data set to the ggplot package, ggplot function. And in this case, we're just going to go ahead and assign it to the plot object. So as you can see, in the current stage, we don't have very much of a plot. If we rerun plot, we can see a little gray rectangle pop up, but there's no additional plotting information done. The reason for this is we're still working very much at that very first abstraction layer. We're just providing our data set to ggplot. We haven't specified what we want on the x, we haven't specified what we want on the y, we haven't specified what kind of geometries or dots or boxes we want present for our type of plot. So this is just the very first laying the foundations so that we can build on them as we go through the plot. And sure enough, if you decide to check behind the curtain using the str function, you can kind of see this output ends up appearing on your console window. So right off the bat, we can start spotting little @ symbols, which is our first cue that we're working with one of those more complicated object-oriented programming style objects, kind of like what we saw for the gating set with the S4 style object. In this case, ggplot is stored as what's known as an S7 object. But right off the bat, we can see that data slot ended up just being filled with our particular data set that we just passed to the plotting object. If you scroll down further, you will end up seeing there's additional slots which are still showing up as empty, which are where we're going to start filling in additional information being provided to the ggplot as we go and build out the rest of our plot. So, having built out this first layer of our plot, we're going to try to build on with the next layer, specifically the aesthetics layer. So in this case, because we want to build a box plot with the x-axis as time point and the y-axis as T-cell frequency, we should specify we want to use those two particular columns for this particular plot. So in terms of adding on an additional layer when it comes to ggplot, basically we start with that function we just used already, where we're passing the data to ggplot. But to add on another layer, ggplot syntax will accept a plus sign, which will then add on whatever the next function to the right of it is. So in this case, for aesthetics, it uses the AES function. And we're basically going ahead and specifying what we want to show on the x-axis and what we want to show on the y-axis, where we're placing time point as x and T-cell frequency as the y. So this is how we end up, and we can see when we rerun plot, it's no longer that little gray circle of gray rectangle. It's now showing time point 0, 4, and 9, and then our frequency scale on the y-axis. So as we add these additional elements, if we go behind the curtains and check, we'll see that STR is also adding things to those slots. So if we go back and check, the little mapping slot is now filled. It's showing what we have on the X being the time point and Y being the T-cell frequency. And we're not going to continue checking STR for the rest of the layers. Just know that behind the scenes, R is placing whatever we have specified in the appropriate slot of the ggplot object. So in our case, we have been building out the plot by just connecting it with a plus sign. However, oftentimes if you're looking at other people's code, you'll see these two layers be combined together. So if you see something that instead of ggplot parentheses data plus aesthetics parentheses, you see it kind of built out together into a single unified argument. So it's ggplot data, comma, aesthetics, parentheses, x equals time point, y equals T-cell frequency. Both of these work exactly the same way. It's just more of how a particular individual decides to write out their building the layer data together. So far, we have not been using quotation marks when we specified the x and the y axis. This is kind of built into what we talked about a couple weeks ago, where the dplyr package is doing something special behind the scene to basically infer that the values that you're providing to it are names in a particular data frame, not something in your actual environment. But what would happen if we were working with a ggplot and we did accidentally include the quotation marks for a ggplot? So if we went ahead and did that for our x and our y axis, you can see this has changed a little bit. Now we just have a single object on the x labeled time point, and just a single object on the y labeled T-cell frequency. So ggplot is not actually able to account for the presence of quotation marks. It's expecting no quotation marks to be present within the aesthetics layer. When you're introducing the quotation marks, it's just kind of messing with it, so it's no longer thinking it must be in your data that you passed. It starts looking for particular object variables at that point. All right, at this point, we built out our data and we built out the aesthetics layers. ggplot now knows that it wants us to use this particular set of data and look at time point and look at T-cell frequency. But now we're at the most important step when it comes to building the plot, namely deciding what kind of plot we want to build. So the geometry layer is that particular layer of a ggplot that will determine ultimately what the plot type is being displayed for our particular data set. So, for example, if you're just going to look at something simple, we could use the geom_point, which is a function that relates to the geometry layer. And let's see what happens when we add this on to our existing code. So ggplot data, aesthetics, time point, and T-cell frequency, we're just adding on a new argument for plus geom_point. So this point, we see the little dots start to be appearing, and we can now see all the little individual rows now being displayed. And sure enough, they're lining up with 0, 4, and 9, the categorical values by which we're displaying on the x-axis. We could do something similar by just swapping out the geom point argument and adding in the geom underscore boxplot to get out a boxplot instead. Just basically switching out what we have in that geometry layer to get a completely different style of plot. And sure enough, we get it. We can see we have this 25th, the median, and the 75th percentiles, as well as a couple outlier dots for that 4-month time point. And similarly, if you wanted to kind of be fancy, but not really be fancy, you could use your geom violin plots, and ggplot2 will accommodate and create that style of plot. So most of the customization for ggplot happens at this geometry layer, and a lot of those extra packages that extend ggplot's functionality are basically building their own unique functions to build different kind of style plots and allow you to implement them. You could also end up adding 2 geometry layers. So what I often do for some of my own data is I'll just go ahead and add a box plot, geometry layer, but then add on the point layer so I can end up seeing both of them visualized within the same single plot. Now, one of the benefits of ggplot being such a massive package and having so many extensions is you can customize it quite extensively, do what you want with it. One of the things I really enjoy is rather than the simple dot plots we can build with ggplot, I often will use the ggbswarm package, which will help distribute them a little bit around the box plot just to make sure they're occupying the space and that we're not losing sight of some of the dots because they're overlapping on each other with same values. So that's what we'll try to build out for the rest of today. So the way we do this is, once again, we have built out the data layer, the aesthetic layer, and we've added on these 2 separate geometry layers, and this is the resulting plot that we have. So you can see it's starting to make progress. We're no longer at that little gray rectangle, but there's still some ways to go. I would like to add a title. I maybe want to change the axis. This gray background needs to go. And more than anything, as I look at this little box is a little bit too much white space, and all these little dots are a little bit too clustered together around the vertical axis. So these are things as I build up the plot that I want to be able to change and adjust as I go. Now, before we go too far on the customization for personal preference, what would have happened if we had left time point as a continuous variable rather than turning it into a categorical factor? So let's go back to that original data. Let's just create an alternate data set, and let's plot it as it was without any actual factoring of the time point column. And as you can see, it looks a little bit different when we start off with the dot plots. It's showing up as 0, it's showing up at roughly where we'd see as 4, and then it's showing up as 9. So rather than 3 equally spaced sections of your x-axis, it's now showing up like if there were actually numeric values for 0, 4, and 9. So while the B-swarm was able to account for this relatively well, when we ended up passing it to the box plot as well, we had something unexpected happen. Namely, instead of being able to account for it, it just gave us back one single large box plot rather than treating 0, 4, and 9 as their separate comparisons and giving them their own respective box plot. So it's not representing the individual groups, it's just looking at them overall. So this is because boxplot is not able to account for the continuous difference. It needs to be given a categorical argument when it's actually doing the creation. So you can't see the warning message for this particular example, but the warning message was actually kind of useful in terms of giving you a suggestion by which you could troubleshoot. So basically it said go back into the aesthetics layer and specify a group set to the time point, which would then allow the geom box plot to actually appropriately create 3 separate box plots. So I ended up doing that, and as you can see, it partially rescued our plot compared to the previous one. We now do have 3 separate box plots, but you'll still notice the bee swarms are around 0, 4, and 9. We still haven't rescued it quite at that level there for everything around. So this example just generally highlights the importance of being aware of what types of values you're trying to plot, as well as paying attention to the warning messages and kind of being on the lookout for quirky, odd-looking plots that may arise when what you assume your data looks like doesn't quite look like what you're passing to the plot, because this is oftentimes the first warning you get as far as what you need to adjust and get things to work. Now, in this case so far, we've been working with functions that rely on having an x and a y, but there's other geometry layers that only use an x or a y axis, so they're single geom layers. What happens if we accidentally end up passing two axes to one of these geometries? So if we're looking, for example, at the geometry layer for geom histogram, and we're still specifying time point and we're still specifying y t-cell frequency, this is the kind of error message you'll get back where there's a problem in computing the statistics, and then eventually it gives you a little error message saying it must have only an x or only an y. But you can just correct that. We can go back into aesthetics, swap it out, only keep the x-axis as t-cell frequency, at which point the histogram function is able to work and generate this plot that we see here. Vice versa, we could do something similar for the geom density function, which does a similar style plot and is able to account for it and build it out as we go. So at this point, we have done a lot of customization when it comes to looking at different functions that will build out our geometry layers. But if we step back and think about what's actually happening in these layers, we're building it out from an abstraction, meaning all the major changes are happening right now at that particular level. So if we're going back in and checking to see what's happening at the bigger scale, those are going to be more the cosmetic end. So if we need to actually change things locally that are going to majorly impact the plot, we need to be able to provide additional arguments that will then build it out. So let's take a look at an example of what we currently have. So in this case, we currently have the two geometry layers currently empty in their parentheses with no actual values being present. So if we wanted to customize these, we're going to have to target them with specific arguments. So the main things I want to target for these two particular ones right now is the box plot is just having too much white space. All the little dots are concentrated right around the vertical axis, and they're overlapping with each other, so I can't really see how many actual dots are present. So how do we go about finding out what arguments we can provide to individual geometry layers? So if we're thinking about how to do this, we just have to remember back to a couple of weeks ago. The way we look up any function information is to go to the help files. So if you're working within positron, you can just hover over the particular function name if it's within a code block, and you'll be able to access the documentation. Vice versa, if you just add the question mark in front of it, the name of the function in the console window, you should still be able to get to a similar output. And same thing happens when it comes to the B-swarm. So it gives you back a lot of different options, but after staring at all the different arguments that we could use, I think I've narrowed it down. I think we should be able to use the size argument to be able to modify at least the individual dots, make them a little bit more noticeable. So as it comes with everything, what I try to do, I just go over the top and try a ridiculous number first, and then I kind of work my way backwards to actually editing it in. So you can see in this case, I tried a size of 5 for my first plot, and rather than kind of achieving what I was trying to do, I made my plot a little bit more nebulous. Like the dots being the size are now overlapping on each other. I can't see separation, so it's not a good visualization overall. But now that I know kind of sort of what to expect for a size equals 5, I can start toning it down. In which case, let's try a 2.5. And as you can see, the dots are larger and they're not quite as overlapping on each other, so that seems to work for the visualization on that side. Now, however, what I would like to do is just kind of make sure they're not crowded on each other. So either I need to shrink the box plots or I need to spread out the dots on the horizontal axis just to kind of keep things a little bit more visually pleasing. So after an additional looking around, I found an additional argument that should work on those B-swarm dots, namely the CEX argument. So let's try that once again, and let's just go ahead and reuse that 5 value. And as you can see, this was overkill. So they're now spreading out into outer space on both the left and the right side. I can't see where one particular group begins and one particular group ends. So 5 was very much overkill. This is one of the things we need to tone it back to be reasonable. So let's once again try 2.5, and as you can see, this is closer to what I was expecting. There's still a little bit of white space when it comes to the 9-month time point, but as you can see for 4 and for 0, they're kind of right in the margins of those borders for the box plot, so I'm actually able to see most of the individual dots with only a couple overlapping here and there. So that is good enough for now. Alright, At this point, we've worked through the data layer, we've looked through the aesthetics layer, we've looked through the geometry layer. The next major layer that will also impact how our plot looks is the scales layer. Now, this is a little complicated to explain right off the bat because it ends up being used differently by different style of plots. So you'll look, for example, at the ggcyto plots that we use for flow cytometry data. It's often used to transform R by exponential axis. Vice versa, what we'll end up doing today is not so much changing an axis, but actually being able to change the shape and the size of particular dots on our plot. So if you think back to what our metadata is currently, we were seeing a situation where we have male and female as being defined within the infant sex identity column. So if we go back and look at what our current plot is, we can see that this current plot, for each individual dot, we can't tell are they male or are they female infants. They're kind of just all clustered together. So what if we applied a scale layer that will basically convert a dot when it's male to being a certain symbol and a certain fill, versus if it's female, change it to look as a certain shape and as a certain coloration or certain fill object. So to actually go doing that is a little bit challenging when you're first getting started. The way you end up doing a lot of this is, as far as how to use proper scale syntax, is look at somebody else's plot and kind of modify it accordingly. So I will put the link in at the end of today. Basically, there's a dictionary lookup for the individual shapes in base R. 22 basically stands in for a circle, and 21 kind of stands in for a rectangle, a square in this case. So basically we're saying if the value within the infant sex column for that particular row is equal to female, make it a circle. And if that value within the infant sex column corresponds to male, create it as a little square. And then we're basically assigning these dictionary lookup arguments to an object we're calling shape_sex. And vice versa, when we're talking how we want to fill in the color for that particular shape, we're basically specifying if the value within infant sex is female, just color it in with white. If the value present within that row is appearing as male, go ahead and color it in as black. And we're just assigning these back to a new dictionary lookup, i.e. the fill sex object variable. And after a little bit of investigation, we can see that we can use two scale arguments at that scale layer just to kind of be able to adjust the dots from what they currently look like and kind of shape them and fill them based on those pre-specified outputs that we already had. Namely, we'll try to do the scale shape manual and the scale fill manual. However, when we are doing the setup, and you can see this is a situation where all of a sudden the line is just too much. So rather than have to scroll massively back and forth a couple dozen times just to see all the line of code that I wrote, if you leave a little plus sign on the right end of your ggplot line and then hit enter, the line will continue on as the second line. And as long as you keep adding plus signs, you can continue breaking this, what would be a huge line, into separate individual lines. And R will still treat this as one line of code. So you're still able to see it, which can be helpful to keeping things tidy, but it will still actually be running as a single line of code. So as you can see what's happening here, I have my data layer, I have the aesthetics layer specified, I got both of my geometries with the particular B-swarm settings that I liked, and then I'm adding on these two additional scale layers, basically referring back the shape to a dictionary for shape_sex, and the fill back to the fill vector for fill_sex. But in this case, we still have a missing piece that doesn't quite work out. So we're getting back this unusual error of error in discrete scale, unused arguments for shape 22, 21. So it's able to see them, but doesn't quite know how to apply them yet in this case. So after a little bit of investigation and looking at other people's plots, what I found out is basically, even though the goal is to have each layer work in isolation, it doesn't quite work that way in practice for a lot of the ggplot2 layers. You still need to interconnect them with some of those important layers like aesthetics or geometries, just so it knows how to apply these particular conversions you're trying to change. So in this case, what I ended up doing is I had to go back into one of those geometry layers, namely the geom B-swarm layer, and I had to add, after a comma, the aesthetics, parentheses, and then I'm just specifying what column needs to be used for shape and what column of the data is being used for fill, so both the infant sex columns. At which point the scale layers are able to properly work, And as you can see, all those little individual dots are now being converted over to reflect was the specimen collected from a male or a female infant. All right, at this point, we've looked at the main building points for a ggplot. We've looked at the data and the aesthetics, which determine which data is being used. We looked at the geometries and the scales, which dictates what kind of plot and what it looks like. The last bits are more cosmetic, just to kind of flesh out additional things that we would normally do. So one of these is facets. So if you remember what we currently have for our current plot, we can see that both male and female infants are being shown on the same plot. But what would happen if we want to break this out into separate plots? Now, we could do a combination of filtering for just male and filtering for just female upstream using the tidyverse packages, and then pass those slimmed down versions of the data to ggplot, but we could also just use the facet layer to just break it out into its own separate plots. So the way this would actually look is basically we're going to use a facet layer function, namely the facet wrap function. And the way this particular argument is going to look is going to be like this. We have all the existing ggplot that we already have, and we're passing it to plus, and then the name of the function, facet underscore wrap. And then we're using the little tilde sign within, which is specified by that function, and we're having it look for the column infant sex, which is what's going to be used to break them apart. So as you can see in this case, we now have a female plot, and then we have the male data being plotted in its own individual plot. We could also do something similar by swapping in a different metadata column that we might be interested in. So in this case, each of these individual FCS tubes was treated with different treatment conditions, control, PPD, SCB. So maybe we wanted to see what the T cell frequency was for these individual conditions. So we just need to go back into the facet wrap, swap out infant sex for condition, and sure enough, we now have the 3 separate plots that we would actually want to visualize, and we can still see the difference. And as you can see, we see male and female infants because we have dictated them based on scale fill and scale shape. Vice versa, if we wanted to condition on the basis of 2 different factors, so let's say we wanted to do it both by infant sex and by condition, we just swap out that individual facet layer function for facet grid, and sure enough, now we end up having females on the top row, males on the bottom row, and then control, PPD, and SCB as the individual columns. So instead of needing to create 6 separate plots, you're able to create it with just one single command. Alright, so far we have built out most of our underlying plot. We can see this is what we're working with, but there's still a lot of things that can be changed that we may want to do in the context of a paper. So if you think about it right now, it's kind of zoomed in on our own particular data based on that y-axis. So all the data that we have is being represented. So we can see all these individuals based on their individual values. But if this plot is going to go into publication and you're going to have many similar plots next to each other, it might be useful to have them actually standardized to start at 0 and end at 100 on the y-axis to kind of keep them consistent across the board. So one way you can do this is basically we need to step back and we need to zoom out the plot so that we're actually able to see it appropriately. So this is where the coordinates layer comes into play for a ggplot object, and namely we'll be using the coord underscore Cartesian function when it comes to specifying these values, which we do in setting the arguments. So as you can see, in this case here, we've added on that new additional layer. We're using the coord underscore Cartesian function, and after looking at the arguments, we can see we need to use ylim is equal to, and we provide that little vector from 0 to 100. And this changes our plot from where it was to now starting at 0 and going up to 100 on the y-axis. At this point, we only have one more layer to explore for today, namely the themes layer. There's also the statistics layer, but it's not something we use directly for this style plot, so we'll touch on that one in a couple weeks. So most of the customizations that need to be done that remain to this plot are no longer the big changes. The data's there, the plot is there. All we really need to do is more on the cosmetic level that are often dictated by personal choice. So this happens within the themes layer. So there's a couple ways to edit a themes layer. You can apply broad general themes where a lot of the authors have already set all these little individual parameters for you, which just apply it generally. But then you also have the option of using the theme function to customize whatever little individual argument you want, just specifying it out individually as you go. So The broad theme adjustments tend to have functions that look like theme underscore something or another. So let's look at a couple of these examples. So as we can see right now, we've switched it out. We no longer have that ugly gray background. We have the plus theme classic, which is applying the classic theme look to everything. So as you can see, the font and the number size has changed a little bit on the axis. We don't have that upper or right border anymore. Everything has been changed out a little bit. Vice versa, maybe this is not your particular style. You could find one of the other 50 or so themes that are preset for you. In this case, this is theme black and white. You can see we now have those upper and right borders again, but then we also have little major and minor grid lines, which can make it a little bit easier to see what value a particular dot may have. Vice versa, you can also set it for minimal, where you have no borders and everything's kind of zoomed in. It really depends what you're actually trying to do with the plot, which of these you might actually want to use. By contrast, or also in addition to, if you like most of the theme black and white, but you just want to make a couple extra additions, you can add on an additional plus theme layer, and then just set those individual parameters you want to change, either silencing them to remove them or modifying them in different ways. So let's say, for example, for that last plot we just saw, we didn't like the major grid lines and we wanted to get rid of them. The way we could do that is we could find what the argument for major grid lines is, and then set it equal to the element is blank function, which will go in and actually remove it. So what this will look like in practice is, you can see at the end of our scale layers, we added another plus, and we set this for the theme function. And then within, we're just basically passing it to panel grid major, which is what sets the panel grids. And we're silencing them by using the element equals blank argument. And sure enough, those little vertical lines are no longer there. However, we still have these little minor grid lines, and maybe you don't want them for this particular plot. So we can also target those once we figure out what that argument is. With a little bit of looking or checking things out, you can see that panel grid minor corresponds to those. And to add an additional argument within theme, all you need to do is include another comma, and just continue adding commas for the additional arguments that get added. And sure enough, we've customized it a little bit. We've gotten rid of those major and minor grid lines in the back. In addition to getting rid of things, you can also modify. So oftentimes we'll encounter issues with access text labels where they are overlapping on each other, kind of obscuring what you're able to read. So one way of being able to get around this is we can rotate them, which will let us be able to read them, and then we horizontally adjust the position until they're back into their original starting position. So in this case, we're just adding in our comma, adding in our next layer argument, which in this case is axis.text.x, and then we're just specifying, instead of blanking something, we want to change it. In this case, we're doing element x, element text, in which case we're saying set the angle for 45. As you can see, these numerics are now angled. And then we're justifying them so that they line up with the little tick mark. And then we're setting the size equal to 16 to show how you would adjust the size on these as well. Vice versa, we still haven't tackled the y-axis. So looking it up a little bit, we can see that that particular parameter of a ggplot is specified by the axis.text.y parameter, and we can adjust the size of those accordingly. And similarly, we can do a lot of adjustments when it comes to our plots. We can change the label on the x, we can change the label on the y, we can change the label up here on the legend so it's not showing as infant underscore text, which corresponds to what it shows up as data frame. We can have it look more professional in terms of what we are actually showing on the plot. Alright, at this point, we have gone through how to do a B-swarm box plot style plot pretty well. Let's quickly, in the last couple minutes we have the class, go back and check on the ggcyto, which is more customizable in terms of the flow cytometry plots. So, if you remember back to week 5, ggplot2 went through a major change recently, upgrading from version 3 to version 4. Because of this, the ggcyto package, which is used to plot flow cytometry data, had a couple bugs fixes that needed to be implemented, and they are now working within the developmental branch. Consequently, until Bioconductor, which does semi-yearly releases, upgrades, we need to go to GitHub to be able to upgrade to the correct version of ggcyto to get everything to work for our flow cytometry plots. Just remembering back, if you want the additional details of how to do this, go back and look at the week 5 lecture, but you should have at least this particular version of ggplot2 and ggcyto. Anything ggcyto 1.39 and above will have the upgraded fixes that you need for your particular plot. Alright, to go ahead and take advantage of this week 5 data set, what you need to basically, once again, load in ggcyto, load in cytomail, which is bringing in the Flojo workspace, repeating the code that we had for week 5, we're just bringing in the Flojo workspace, putting it into a gating set, and once we have the gating set, we can basically go ahead and build out our plot. So this is using the ggcyto package, but let's now use what we learned about the ggplot2 package to kind of see how this particular syntax is structured. So as you can see, we still have kind of equivalent of a ggplot2 argument. We have the ggcyto argument, and we're passing it a particular data, namely the 6th object in our gating set, specifically the T cells. So that kind of stands in for our existing data set. But then we're providing an aesthetics argument, basically saying we want the CD8 and we want the CD4. And then to that one, we're passing it on to an additional layer being added, namely the geome hex layer, which is kind of working like a geometry layer, which will get us as plot, providing bins as the argument. So if we look at the plot right now, this is what we end up getting. But just to let you know, a lot of those same kind of abstraction layer arguments we learned for ggplot2 will also work for ggcyto. Not all of them, because ggcyto is still a different package. It does stuff differently in the back end. But as you can see, when I add theme black and white, I ended up customizing what used to be the gray background of this particular ggcyto plot, and we're able to actually work with it. So things that you can play around with and try as you learn ggplot2 syntax is try to use it also in ggcyto and see what works and what doesn't work. If there's something that doesn't work using ggplot2 directly on ggcyto, oftentimes if you convert your ggcyto object into an actual proper ggplot first, then you can actually come in and do all the customizations that you may want. And we'll look at that more over the next couple weeks as we start visualizing flow cytometry data regularly about how the customizations we can do. The takeaways for today. We have looked at the grammar graphics concept, looking at how we can abstract things into individual layers, and then combine these different layers and different arguments that target them together to make the actual ggplots that can do a lot of different things by just modifying little individual plots accordingly. This allows us to generate a bunch of variety of plots, keeping kind of a similar language by which we can build them, and just adding in the bits and pieces as we go. Next week, we're going to take a little bit more closer look at how to modify the ggcyto plots to visualize differences that happen when we're applying different transformations, i.e. the different scalings, and we'll try to touch on compensation, at least in the context of conventional flow files, although it's going to be a little tight trying to cover everything, so I'll see how I square that circle next week. And with that, we are out of time. We're ending a little bit early, so if anyone needs to go, feel free. Additional resources for today. There's quite a few because ggplot2 is a large package and there's lots and lots of documentation for it. One of the resources I recommend is Elegant Graphics for Data Analysis by Hadley Wicken, Danielle Navarro, and Thomas Lynn Peterson. Many of the authors are actually the ggplot2 maintainers. It is an excellent resource that's good for both beginners and advanced users alike. So if you have a general interest in how ggplot is built, this is the place to go. Additionally, there are many R Ladies groups worldwide that host monthly meetups talking about particular R topics and particular R workshops. Many of these workshops get posted monthly online on YouTube, and they can serve as invaluable resources for those who are just getting started as far as how to actually do things in like ggplot. So the R Ladies Paris did a particularly good introduction to ggplot workshop, which I'm linking here. Similarly, Kara Thompson goes above and beyond when in terms of making her ggplots really, really excellent, like actual high-end magazine worthy. So any video by Kara Thompson is one I recommend. Level Up Your Plots was a workshop she gave for the Harvard Working Group, so I've linked it here as well. And then TidyTuesday is a weekly data challenge where basically you're given a completely brand new to you data set and you're asked to generate the best visual summarizing the information contained within that dating set. This is what very much those data scientists who have all that extra pay and time on their hands end up doing, but it's a really good place to go when you actually want to like see how to do a particular style of ggplot. It's a good place to go for inspiration, and it's a fun challenge if you do have the time on your hands to be able to do it. Take-home problems for this week. So far we've been mostly focusing on those B-swarm style box plots, and we use time point in this particular condition. I want you to have some practice like swapping in other metadata for the particular columns. So I would like you to try to at least swap out time point for condition. And because, as you saw, some of those geometry, aesthetic, and scale layers are kind of built in on each other, it's going to error out on you in the first attempt. Just try to build out until you get kind of the equivalent plot looking for condition, and then just try to see if you can flip around instead of control PPD, SEB, try to rearrange the axis in a different manner. Problem 2 is kind of exploring onto this ggcyto flow plot. Modify it until you are kind of content with how the visual appeal is. This is actual code you'll use continuously throughout the rest of the course, so it's worthwhile tinkering with it. And then the third problem, which cut off at the bottom, basically, we saw this one-dimensional histograms and density plots. Try to break those apart to actually show individual groups also on a one-dimensional. So like show male and female as their own separate histograms that are visualized. That's the third optional take-home problem challenge. And with that, that is what I have for today. If there's any questions, I'll be in the chat for a little bit. If not, I'll see you on the discussion forum, or I'll see you guys next week when we start talking about how to do transformations in the context of a gating set.